First three. Can you see?
Yes, we can
Okay.
see. This space bar wasn't working, but now we can see. We
Okay.
can see. That's right.
So, good morning. Thank you for joining us to the third lecture. I'm I'm going to start with a brief summarize of the last lesson. I mentioned that we're going to study the early universe in the epoch of inflation, but yesterday you asked me many questions at the end or even along the talk, and I try to answer your questions in the middle of the talk. And also I'm going to study a new part of the I'm going to show you how the people study cosmology without inflation, and then how they incorporate inflation in order to explain the primordial cosmic structure. So let me say something about the problems before inflation. Yesterday, we saw, or we realized, that this was one of the problems, the horizon problem in the model, in which we have two regions that an observer today see with causal connection, but when the people study the dynamics according to the cosmological model at that time, they realize that they having reasons to expect that the two regions were in causal connection, but they put the question on the table and try to answer what is a good physical effect to explain this relation, and they introduce the paradigm of inflation. It's an epoch in the early universe in which the universe suffer an accelerated expansion. In that sense, we're going to proceed with this study. This is a picture to represent what happened in the early universe. As I mentioned yesterday, we thought this patch after the Planck era, and this patch started to inflate and generate the expansion and generate the structure as today we can see. Okay, I add now. Yesterday I add this slide before sending you the full presentation, because it's important mention that Alan Wood was one of the pioneers in this field. He introduced the period in the model to solve the problems, for example, the horizon problem and the monopole problem. But with the pass of the years, cosmologists realized that one of the advantage of this period is not only give a solution for those problems, is the main advantage is that inflation in cosmology give the good explanation for the primordial cosmic structure. But let me tell you in terms of math how we write this effect in the early universe. The model is described by this action, that is the Einstein-Hilbert action with a new term. In this case, is a scalar field which characterize the matter sector. The name of this scalar field is inflaton, and it's responsible, this field has the responsibility to inflate the universe using this potential. As I mentioned yesterday, this potential could have many forms. One of them is the harmonic oscillator potential, is one of the easiest potential to work, and we know that according to the observations in a particular theory, the harmonic oscillator potential still works. And the space-time is described by this metric. This metric now has two components. The first one is the background. This is the geometry that we studied in the first lecture, is the Friedman, Lemaitre, Robertson, Walker, and then we're going to add this part that talk about the perturbations in the geometry. The background I write here again in terms of the conformal time, and the inflation field is expressed by this equation. Yesterday, I mentioned, or I tried to emphasize, that this first term is independent on the position, is the mode responsible to generate the expansion, and the other modes are the responsible to generate the structure. So in this session, or in this full class, I'm only focused in the characteristic of inflation and in the characteristic of the generation of the structure. I only mentioned the horizon problem to motivate or to illustrate one of the reasons because inflation was introduced in the model. And why use conformal time instead of physical time is a good question. In this case, it's only to get easy the calculations, but also in many times when it's not just the case here, but yes, I have a previous example. For example, for instance, in this case, when we draw the null trajectories using conformal time, we could use the lines to 45 degrees in this case to illustrate the horizon problem. But in this case, I use the conformal time only to simplify the calculations. But as I'm going to show you that when we are interested in the physical situations, for example, how the what is the behavior of the zero mode of the inflation field? When I try to study the dynamics of this quantity, I need to rewrite the equations in terms of physical times. So it's a good question because I can use this new variable to get easy the calculus. But when I perform an approximation, or when I take into account a physical situation, I need to back to the physical time. And I can show you that, for example, those are the assumptions of the model that I mentioned. I thought that the mode that is turned on is the zero mode of the inflation field, and the other modes are in the so-called Bunch-Davies vacuum. In this case, I'm going to work with this potential, and the relevant Einstein equation and Klein-Gordon equations are those equations. And as you can notice, those equations are right in terms of the conformal time. Actually, if you write the equations in terms of physical time, you're going to realize that the only change, if I remember well, is one factor here, and is the one factor here, and if I remember well, this equation remains without change. And the only change is in this part, because instead of have 2, we have 3. in this part. And okay, then we have this quantity, and is the, as I mentioned yesterday, is a Hubble term. In physical time, it represents the expansion of the universe. In this case, it's not exactly the expansion. If we want to study the expansion, we need to back to the expression in terms of the physical time. But at this point, it's useful to represent with this symbol because it's the analogous to the Hubble terms in terms of physical time. Okay, so this is only the last class in a nutshell. And yesterday, yes, go ahead. Okay. Do you have any question? Or maybe, okay, I'm going to continue. And if you have a question, please interrupt me. So we have these two dynamical equations, and those equations, we can read the dynamical of the early universe using those equations. But what we should have in mind, the idea. Yes. Please go ahead. Or also you could write in the chat. Okay. So the physical idea, as I mentioned yesterday, is the following. I thought I had put the picture in the slides, but it seems that no. Actually, I'm going to use a new blackboard only to draw the same picture as yesterday, but the mechanism is the following. We thought this potential as an effectively cosmological constant. And we thought that the zero mode of the inflation field behaves as a point particle. It's a naive way to think in the zero mode of the inflation field, but this effectively cosmological constant, when the inflation starts in this point, to say something, the value is biggest compared with other points down to this point. So we thought that this zero mode of the inflation field roll down to the potential until to reach the minimum here. But I need the physical equations to describe the dynamics which carry this particle from this point to the minimum. And this scenario is the slow roll scenario. And we're going to use the Einstein equation and the Klein-Gordon equation. And we add an assumptions on the equations. Let me show you. The equations are those equations, but as I mentioned, this factor contribute as an effectively cosmological constant. And this cosmological constant, when the inflation started, within that this term is bigger compared with the synthetical term. Okay, when we compare the velocity with the potential, we can have in mind that when inflation starts, the dominated term is this. The potential is bigger than the derivative of the zero mode of the inflation field. And I put the assumption here in the two. And also, we're going to consider that the zero mode of the inflation field behaves like a particle, as I try to illustrate in this bad diagram. And this particle suffer its terminal velocity. And you can remember that the terminal velocity in mechanical books or in mechanical physics is right in terms of the second derivative equal to zero. It means that the force is, the friction force, for example, is equal to the velocity. So in that sense, I represent that physical situations with this equation. And also, as one of you mentioned, someone mentioned, why the reason? Because you are working with conformal time and not with physical time. Okay, because at that point, I only presented the Einstein equation and the Klein-Gordon equation, but now I'm going to take into account the physical part of the physical process that the zero mode of the inflation field suffers. So in this case, I need to rewrite the equations in terms of physical time. And if I want to work with if I want to continue using the conformal time, I need write first this equation in terms of the physical time and then map to the conformal time as I did here. Okay, but let me take the equations. For example, we're going to apply this condition in the Klein-Gordon equation. So I mean, first of all, I need to write the condition of the terminal velocity in terms of the conformal time, but I have the equation in 7. So I have the conditions in terms of conformal time. Now I'm going to replace this quantity. I can see the number because I see your faces. So, okay, it's equation 7. And I'm going to replace here. And okay, let me show you. In this case, instead of write the second derivative of the zero mode of the inflation field, I'm going to write the condition for the terminal velocity. And this is the term that have the condition. Remember that these terms talks about the expansion, how big is each slide, and these terms is codify or encode the expansion. So this is the term responsible to the friction part of this analog to the particle behavior for the expansion. This is the Einstein equation. And the red part is the terminal velocity condition. From this equation, I'm going to get an identity between this h, because if I zoom, you can see this is only this part. And from this, you can read sorry. This is the first time derivative in terms of h, and in many books, you have this expression only to represent how change this term. This is this codifies the movement of this particle, and you can see that this sign tells me that the particle rolled down this potential, and at the end, it reached the minimum, and we have a damped factor, which is the expansion. And the expansion is related with the gravitational effect. And also we have how this potential changes according to the zero mode of the inflation field. Okay? And those quantities are dependent on conformal time in this case, but we can get the physical time. And the second condition, only, let me show you oh, sorry. In this case, in this equation, I put the terminal velocity. And now if I consider that this term is bigger compared with this, I can drop this term, and I only have a relation between this h and this v. So I obtain the following identities. This identity, this h initial or h appear in many references as a capital H without the dependence, but sometimes there are many confusions, because in the books it's not usual that appears with this factor, but when you see in the text only the H without the dependence, the people talk about this term, not the term responsible to the expansion. So be careful, because there are many similar symbols as the H that is dependent of the physical time, which is the responsible for the expansion, and this H that is the analogous term, but in terms of the conformal time. And we have an additional term that is this term. I know that sounds trivial, but actually in many references or in many manuscripts, you can find several mistakes about this quantity. So be carefully when you talk about the expansion is with the physical time. To perform the calculations, or to perform or get easy some procedures, you can use this expression. And also this expression could write in terms of this hi, which is related with the condition that the potential is bigger than the kinetical term. So it's important, because sometimes if you are working with this expression, you should keep in mind that you did or you perform an approximation. And the approximation is that you're thinking or you're working in a really early epoch. In an early part of the inflation. In the beginning of the inflation, this assumption is true. It holds. Because it comes to manage these terms, and I get the equality between this part and this part. And now we have the equation that I mentioned represent how the particle roll down the potential, and in terms of the factor of the expansion and the factor which codifies the size of each hypersurface. In many references, you can find that this displacement is known as classical displacement. I mean, we have this change between the zero mode of the inflation field along the time, during the pass of the time, and what could be a good notion of time here could be a question. And you can find many ways to measure the time, but one natural scale in this context is the notion of the Hubble time. Yesterday, or I'm not sure if yesterday or in the first class, we got a review about the Hubble radius. The Hubble radius is right in terms of h, is the inverse of h, where h is this quantity, but with the physical time, and the Hubble time is right in terms also of this quantity. So one natural scale to measure the time is the Hubble time, but it's not the only one. And I realize I'm not sure if there are questions in the chat, but I'm going to continue. If you have any questions, you can ask me, please, in this point, because I'm going to move to other topic. So far, do you have any question? Any questions? Okay, it seems there are no questions. I don't understand the meaning of the displacement. Okay, let me show you, and let me summarize those kind of things. I started with an action, and the action codifies the expansion of the universe using this effective cosmological constant. From this action, we have two equations, the Einstein equation and the Klein-Gordon equations. Those are the equations that we extract from the action that I presented. But what is the physical situation here? The only mode responsible for the expansion is the zero mode of the inflation field. So those equations, if you see, those equations are right only for the zero mode of the inflation field, not for the full inflaton. Only are equations only for the zero mode of the inflation field, and the situation that we try to describe is how, with this equation, we could explain the expansion. I know this V play the roles of an effective cosmological constant. And let me show you the blackboard. And what is the physical situation? I want to describe that in the beginning of the inflation period, the universe experiment an accelerated expansion, but it's important according to the observations and with the facts that we know about our universe that that kind of expansion end. So the mechanism that the people in thought, or the people thought in the following sense, I I imagine. Okay, I need a mechanism to dilute the inhomogeneities, the anisotropies, but also I need that such mechanism turn off at the end of that period. So the situation that they incorporated is the following. They thought I have a potential, a cosmological constant, but it's not exactly a constant because I thought that this particle, as the name of the mechanism, is slow roll on this potential to reach the minimum of the potential. Why is the reason? Because I focus in the displacement that I mentioned. It's because I want to describe the situation in which in the beginning I have a big cosmological constant, but over the time process, this cosmological constant slowly decreases and decreases in a slow way to reach the minimum of the potential. And in this point, the cosmological constant is zero, but and leads to the inflaton continue, and the next epoch should describe how this inflaton decays in the whole standard particle model, but this is a different epoch in the universe. I'm previous to that epoch, and I try to describe the dynamics to this zero model of the inflation field. So using the equations, this is the Einstein equation, I put the fact that I thought in the situation in which the particle get the terminal velocity. The terminal velocity, as you can remember, is when the particle, the friction and the velocities are equal. So I have this condition. Sorry. But this is in terms of the physical time. And the only thing that I did is write this equation in terms of the conformal time. And this is the condition in terms of the conformal time. I put the condition. What is the condition? That the particle suffers the terminal or reach the terminal velocity. And I put the first approximation here. This is the first approximation, and it leads the next equation. This is the equation, and you can read, you have the first time derivative of this zero mode of the inflation field, which depends only on time. And as in many equations in physics, this is related with a velocity equation, maybe, or the question could be in terms of, if I write this equation, or I consider this equation over one period of time, I talk about this, how put this time. One can consider this time as a Hubble time. If I consider this situation on a Hubble time, for instance, I'm going to get the notion for the displacement quantity. More or less. Can I, someone, okay, so here I have the equation, maybe that was the question, let me know. But this is an equation for the velocity for the zero mode of the inflation field. And using the velocity and considering the velocity over one period of time, for instance, the Hubble time, I can get information about the classical displacement, and this equation that I wrote in the presentation. Sorry. Is this right? This is the classical displacement. I use this symbol to represent the classical displacement, and is right in terms of the equation in which we take the terminal velocity approximation. Okay. The second approximation that we took is the fact that also in the beginning the potential is bigger comparing with the velocity terms. So it allows us work with this equation. So in many, so far I only use to get this equation, I only use the terminal velocity approximation, but in many other cases for interest, you can read this equation. And it's good to know that this equation or this identity implies take this approximation, that the potential is bigger than the velocity. So it's important to see in which part of the inflation you are working, because it's not hold in the, it holds almost in the whole period, but it's important verified. Cosmology has advantage and disadvantage as many branches of physics. And I hear many times in cosmology, you have many approximations. And okay, take approximation is not bad, but you should know what kind of approximation you have considered. It's really important know that kind of approximations to justify the physical process here. So with these equations, now we have a mechanism known as slow roll mechanism in the inflation paradigm to give an explanation of the expansion of the universe. So using such mechanism, we have the justification to say that in the beginning we had a patch, suffer inflation, and reach a bigger patch in which the inhomogeneities and the anisotropies were diluted. So this is one of the features that I wanted to show you, but there is a second important part in this paradigm, and is the explanation for the primordial cosmic structure. As I mentioned before, to work with the primordial cosmic structure, it's important write all in terms of the perturbation in the perturbation theory. Why? Because we start with a patch with inhomogeneities and anisotropies, then you have an effect or a physical process which dilute such inhomogeneities and anisotropies. But now you need again to incorporate a mechanism or a different physical process to explain the primordial cosmic structure, because if you don't take into account this part or this part, you are still in an homogeneous and isotropy universe. But when you consider this part in the geometry, in the geometry of the universe, and in the matter sector, now you have the ingredients to start to work with the structure. But first of all, I want to talk with you what was the explanation for the structure before inflation. So I apologize because it's not in a chronological way, but according to the question that yesterday I heard or I read, I thought one idea is introduced. First of all, the spectral characterization for the matter, and then tomorrow try to connect this spectral characterization with the quantum analysis. But let me tell you what was the mechanism to explain the spectral characterization before inflation. I use this date only to emphasize that was the year in which the inflation was incorporated to the cosmological model. But the people, as in many other topics in physics, try to characterize the structure with a spectral characterization. This I meant they use Fourier transforms of quantities important in cosmology. I'm going to use this notation as in Weinberg and other books used. It's a way to represent a generic quantity. Here is generic. I haven't put a specific characteristic on a system, but what could be a possible quantity to describe in terms of Fourier transform could be the density, for example, or the pressure. And the quantities are right in the Fourier transformation as you have worked before, for example, in electromagnetism or in statistical physics. Okay, and what is the idea that they had in mind? In a generic way, the coefficients could take certain values, but in this case, in cosmology, the coefficients are thought as representatives of assembles. And assembles of what? The people thought in an assemble of possible universe. I know there are words that sounds we should be carefully using the names, but it's only a mathematical tool to get the spectrum of one quantity. In this case, they take into account an assemble of possible universe only to characterize the distribution and the coefficients for this spectrum. The statistical distribution for these values taken as representatives of symbols are defined with this quantity. In this case, this P denotes the power spectrum of this quantity, which is still being a generic quantity. But I mentioned the possible candidates to describe, for example, the pressure, the density, to describe the full spectrum. And again, the line over this quantity, where this represents the complex conjugate, and the line represents the average over the ensemble of universes. And the universes are the top possible universes that the people consider to perform the analysis. Okay, it's only a statistical tool because we know that with you have only one universe, but to perform the calculations, you can take into account the possibility of have a collection. And then the people, I try to say Harrison and Seldovich gave a proposal for the spectrum of the matter using the spectral characterization. They gave a proposal only by hand. They try to argue that the spectrum for relative density perturbation, so they put a specific quantity here. I was using a generic form only with the aim to illustrate that this could work for many quantities, but Harrison and Seldovich gave a particular quantity, the density perturbations. The density perturbations can be written in the following way, and this quantity is dimensionless, and they thought this spectrum that we're going to introduce should be in the remote past with this form. And this is the form that they put by hand. It's not only write an equation and that's all. They try to connect with the observation that they had at that time. In this case, this A represents the capital, this, yes, is the only one A, but it represents a dimensionless constant, where this L represents a length, a characteristic length of these quantities that they take into account. And this L is a length which depend on this N, which codify or try to give us an intuition of the dimensionless. So we're going to consider the case, not the dimensionless, sorry, the scale notion. This N play the role of the scale. Sorry, I used the bad word. But the N here and the N here. But this spectrum try to describe the structure in the universe. But they thought, okay, if we want to study the structure, we need consider that the behavior or the spectrum of the structure shouldn't depend on the scale. In that sense, they try to figure out what happened in the cases in which or what could be a possibility for this quantity to get this quantity without the dependence of the scale. And they realized that when study a particular case of N equal to 0, they get this spectrum. So for that case, they have this quantity and they get this part for the spectrum. It's a spectrum in which they don't have a notion of length because this quantity is equal to 1, and the full power spectrum is scale. The people say that this spectrum is scale invariant. So for the fact that they could characterize in terms of a spectrum using the Fourier transformation, Then they thought, what could be a good measure to characterize this spectrum, sorry. Can you see my? Okay.
We still see the averages. Is that what you
Yes.
wanted to show us?
Yes, I lost the. Yes, I have again. Sorry.
Okay.
We have the Fourier transformation, the spectral characterization. The people ask what could be a good candidate to represent this spectrum, and one of them, not the only one, is the fluctuations over the density. As Harrison and Seldovich wrote, this is the relative density perturbations, and they try to describe the spectrums using the density perturbations. This is for one side, but for the other, by hand, they try to give a form for this spectrum. And they thought, what is the distribution of the matter? I need a form for this spectrum to take into account the formation, for instance, the black holes, the galaxies, the stars, the planets, but also they consider a form in which the structure changes under the time. And okay, and then one of the questions was, okay, I know this could work for study the matter structure, but I need another feature on this quantity, and is the fact that we expect the study of the universe is independent on the scale. In that case, they try to figure out an spectrum, and a scale invariance spectrum. And one way to represent that invariance is using this n equal to 0. When they consider n equal to 0, they got the form that I presented here. This is the power spectrum for in the cosmological structure, and we are interested in the case, in this particular case, for this spectrum. And actually, nowadays, the people try to get this spectrum with n not exactly 0, but close to 0, because nowadays we know that the universe is not exactly scale invariant, but it's not, but the dependence on the scale is small. So they try to get a properly n to get with precisions the observations in the power spectrum. So this was the power spectrum, but you can see here, this is a constant, and in this case, they try to represent a form on a particular case. In this case, this case represent only a particular election on this distribution, and it's really, really important talk about this analysis, because if I remember well, in the only or at least I only read this analysis in the Weinberg's book, but they try to emphasize in distinguish between some kinds of notions, between the statistical part, and then to the distinguish with other kinds of features, as we going to see tomorrow in the quantum analysis. But here you can see that this K is related with the fact that we going to consider an average. And the average is an average taken as on the ensemble of a top possible universes. As I mentioned before, we know that we we only have one universe to study the observations, but the people, in order to perform the calculations, try to incorporate the notion of an ensemble. They write equations in terms of this generic quantity. In particular, Harrison and Seldovich, using the density, relatively density perturbations, character which has a level k, in order to get an average in the Fourier transformation, the level for the Fourier transformation for the spectrum. And they got this form for the power spectrum. This form in the power spectrum represents the generic form for the structure in terms of an scale invariance notion. And yesterday, one question was how the people connect the primordial fluctuations with the matter. What is the way in they try to connect? It's a full course, a former course, maybe not former. It's a I mean, I try to say that in one class is really hard cover all the details to explain these features, but I try to summarize and give you the references to study by your own this part. But let me try to clarify the questions that yesterday you had. And we know that Harrison and Seldovich gave this form for the structure. And we have observations. The most remote data that we have is from the CMB, the data from the structure. So using the CMB, if we read the signals from the CMB, we can read the most remote, the remote past of the structure of our universe. And if we take the spectrum of of Harrison-Seldovich, we can study how the primordial fluctuations evolve on time. As I mentioned before, the quantity that Harrison and Seldovich considered here, for example, instead of put this generic quantity, they use the relative density perturbations. So this spectrum could be thought in terms of the density perturbations. And the people try to connect this power spectrum with the observations and try to study how the perturbation or the primordial fluctuations evolve. They thought, or they were taught in a period in which radiation were the primary component. In the case of inflation, as I mentioned before, we focus in the cosmological constant, not in radiation, okay? It's different. In this case, the people, or at that time, the people thought that the universe was filled with radiation. And they thought, okay, we need to take into account the primordial fluctuations characterized by this power spectrum and study how they evolve. But they also was not trivial, as you can see. They took into account also the plasma effect of the baryons, the electrons, the photons, and the perturbations of dark matter. So they thought, maybe not properly in data of not just in the dark matter, but they consider as a dust. And they try to see what happened with the primordial fluctuations. Okay, I don't know why at this point I could put this. I put this picture before, but this is the well-known CMB map. They try to study the temperature in different points in this sphere and try to see how they are connected. You can see that you have the quantity, the power spectrum that depends on this K, depends on time, and intrinsic has the assumption that represents an average on a big collection of universes. And from this map, the people can extract the temperature of different regions, and we can detect the people detect the photons emitted from one surface. You can think the surface as one of the slides, as we can see in the first lecture. That slice is characterized by a particular temperature that I wrote here as 3000 kelvins and is known as large scattering surface. So the remote path that we can read, or the remote data that we got from CMB, is from this surface. And this was the question: what is the role that the redshift plays in cosmology? And I try to connect that question with the question about the fluctuations. So the people try to read or try to detect the photons emitted in this surface. And then they try to study the redshift in these photons, but they suffer this redshift by the cosmological expansion, as we studied in the first lecture. And this is the temperature that the universe have today. And also they try to compare, I put this name, but we're going to study, I'm not sure if today, but maybe tomorrow. The Newtonian potential is a quantity that appears in the perturbations of the metric. So they try to study, so they try to figure out what is the redshift of the photons emitted from the CMB, and also try to connect that quantity, the redshift, with the temperature that they obtain reading the temperature of different points in this whole sphere. And they study also the local variation on temperature to study a different topic, that is the relative abundances on atoms in photons. If I remember well, in the chat appeared one question about that in the first lecture or yesterday. I don't remember. But basically, the people study the redshift that the photons on this surface suffer by the cosmological expansion. The temperature that the photons had on this surface is this, and the temperature that we have today is this. So with this change of temperature, they try to connect the change of temperature with the expansion of the universe using the redshift. That was the reason because I started giving an intuition of what is the redshift in cosmological scenario using a light signal, because the element that the astronomers and cosmologists study are just light signals, because they study the photons and they try to study the characteristics of the redshift in terms of the frequencies or in the energy, and also try to connect that that quantities with the difference of temperature, because from those kind of data, they obtained the difference between the temperatures and then try to connect with the redshifts. So sorry again, because this potential usually is represented by this part, and is related. I think I have in the, let me, sorry, sorry for this. But when we consider the perturbations on the classical background, we focus only in this part. The perturbations on the metric are right in terms of this quantity. If you are attended the perturbation course after this, could be help you, because in this case, I only use the final result, but the people consider scalar perturbations for the inflaton, and they consider the perturbations on the metric at the scalar level, at the first order level, sorry, and they choose a particular gauge. It's known as the Newtonian gauge, and this is the well-known Newtonian potential. The Newtonian potential codifies the perturbations on the background. So it's the quantity that tells us about the perturbation in the geometric part. And this quantity is also useful for the observations, because the people try to, or not try, have the results in terms of the temperature and the relative fluctuations on the temperature, and they try to connect with the Newtonian potential. It's a way to connect the observations with the theory. And this result is obtained from one experiment. I forgot to write the name here, but I'm going to add, is the Sachs-Wolf effect. And they realized that the connection between the temperature and the Newtonian potential using the redshift gives this condition. So they had actually, previous to incorporated inflation in the cosmological model, they had a way or a notion to study or to connect the theory with the observations. You can read from this picture that they studied the redshifts and also write in terms of the spherical symmetry. So they use the harmonic spherics to represent the difference points over the CMB sphere. That is the reason, because sorry, but this represents the polar in the case of theta, and the azimuthal part is about election, because I wrote the inflaton also in terms of this letter. But it's important to know that this is the part for the angle, not the azimuthal angle, nothing related with the field. And they try to compare the quantities, the whole points over the whole sphere, with the Newtonian potential. This quantity, as I mentioned before, is a quantity which encodes the perturbations on an homogeneous and isotropy universe. And we try to study, or try to refer the Newtonian potential as the intersection between the observations and the theory. And also we can think, or we can have in mind, the idea that the Newtonian, we refer to this potential at the intersection on the last scattering surface with our past-like cone. I don't know if you have questions, because I can't see the chat. I lost the chat. I don't know what I did. But if you have questions, please go ahead. I'm going to follow, mention one difference between a kind of notions. We have in this class, we study the spectral characterization. This characterization was useful before the inflation, and actually it still works very well. But I try to say that it's independent to the inflationary paradigm. And also, it's a characterization that gives us the spectrum for the matter distribution, and the people had a result to connect the distribution of matter according to the observations with the theory using this equality, and they reproduce the spectrum. But it's important, as I mentioned, in cosmology, know the full considerations that we take into account. And let me clarify what happened with the fluctuations. This distinguish between the fluctuations is a summarize of a discussion that appeared in the Weinberg book, and he tried to put clearly the different notions about fluctuations. There are three well-known kind of fluctuations, and I'm going to start with the B, because the statistical fluctuations, as the fluctuations that Harrison and Seldovich consider for their spectrum, are known as statistical fluctuations, as pre-Escher statistical fluctuation taken in an ensemble. Those are associated to an ensemble, as the case of the pre-Eschers or the density, and each element have a different value. I mean, have a different weight, as in the case of the ensemble for the densities. So if you have a big collection of objects, you can think that collection in terms of an ensemble, and the whole ensemble have a characteristic for each element weight with one factor, and that in that case we talk about the statistical fluctuation. So when we have in mind the temperature, for example, but over a big collection of objects, it's important realize that we are talking about the statistical fluctuations, and it's completely different with the space-time fluctuations, because in the case of space-time fluctuations, we only refer how a measure or a quantity change from one point to the other. For example, the same case could work, the temperature, if I measure the temperature over an object in one point, and then measure the same quantity in a different point, and I consider the change between them, I think in a space-time fluctuation, even if I work with the same quantity, that is the temperature. But in the case of statistical fluctuations, it's really important have in mind the idea that we have a big collection of objects, or we have an ensemble. it's different. In the case of the Harrison-Seldovich approximation, they consider the both fluctuations. First, along the quantity, how change on the space, but also they consider an average. And they consider how change when they took into account the ensemble of possible universes. So they have in mind two ideas of fluctuations. One, regard to the change, how a quantity change over the space, and is this the space-time fluctuations, in the sense that in many times we consider in GR the whole space-time, and also you can have the statistical fluctuations, how the quantity, how are characterized by a weight factor. But for that case, you need to have an ensemble, or in other words, a big collection of objects. In the case of cosmology, the people thought on a collection of universe, but you know, it's only an idea, it's an hypothesis to work with this assumption, but in practice, we only have access to one universe in the case of the data that we have. And those are the fluctuations related with the Harrison-Seldovich spectrum. But let me introduce a new kind of fluctuations that we're going to study tomorrow, the quantum fluctuation. But it's not, I'm sure that is not the first time that you are that you study the quantum fluctuations, because maybe are familiar with these kind of fluctuations, because you can remember for the quantum mechanics course that if you consider the wave function of a system, for example, the harmonic oscillator, if you talk in the ground state of the harmonic oscillator, you can think that you have a Gaussian form for the ground state, and the ground state is described by this Gaussian function, and the weight of the Gaussian function talk about the uncertainty. Let me draw a simple form. So you can think center it here to say something, or let me put this only to represent the way. So the fact that the wave function for the ground state have a weight implies that this quantity is related with the quantum fluctuations. You have a weight in the wave function, and this way weight represent the uncertainties, because as you can remember from quantum mechanics, we know that we don't know what is the exact value for the quantity. At least you perform a measurement on the system, and in that case you get a particular value, but in that case you say you need to collapse this wave function and get a particular value for this case. But this is only a way to introduce the quantum fluctuations only refer to the uncertainty. I meant we don't know what will be the value in this case until you perform a measurement to collapse this wave function and get a particular value for the quantity. So at this point, you only have a wave function with a weight, and the weight represents the possibility, the uncertainty to get a particular values. And that uncertainty is known as quantum fluctuations. But it's important to emphasize that quantum fluctuations only describes indeterminacies on some quantities. For instance, the ground state on the harmonic oscillator, but it's completely different in the case of statistical fluctuations, because statistical fluctuations are thought in a sense of a big collection of objects and have a weight for a particular quantity on those large collection of objects. So in the case of quantum fluctuations, only the quantum fluctuations are related only with the uncertainty, with the fact that we have the possibility to get different values, but we don't have access to that values until you perform a measurement. But are completely different for the statistical fluctuations. So tomorrow I'm going to present how the cosmologists obtained the power spectrum with the same form as Harrison and Seldovich got, but using or taking into account the inflaton, the perturbations on the inflaton, as I wrote here, and the perturbations on the background. So they study what they ask yourselves. I thought, okay, we have a tool or a paradigm to solve the naturalness problems as the horizon problem, explain how the universe turns into an homogeneous and anisotropy universe, but we have this spectrum that works very well, the Harrison-Seldovich spectrum, to explain the structure. So they expect that the inflation paradigm could solve also the problem for the structure. And they had a good impression on that. And tomorrow I'll show you how they obtain the same spectrum using a quantum theory on the, or quantum field theory. Using quantum field theory, they reproduce the same power spectrum for the primordial cosmic structure. But also tomorrow at the end, I'm going to discuss with you the several problems, or try to connect the problems that the first glance seems philosophical problems on this paradigm. But in the last lecture, I showed you a particular problem that is not exactly a philosophical, is a philosophical problem, but how a philosophical problem could imply in the physical part of our analysis. So for now, let me know if I answered your questions about the CMB, how the CMB data is connected with the power spectrum using the redshift, and what the symmetry that codifies this equality, and how And what is the distinction, and which is the distinction between the quantum fluctuations, statistical fluctuations, and space-time fluctuations? It's important put emphasis in the fact that the horizontal Dovich spectrum use this quantity, this relative perturbation, a quantity that change on the space-time, and also they consider the average. And when they took the average, they were considered the statistical fluctuations and the space-time fluctuation, but at this point, they haven't considered the quantum part. Tomorrow, we're going to describe what is the reason, because the people said quantum fluctuations could give us the explanation for the structure. Tomorrow, we're going to have a discussion about quantum fluctuations. What are the, I present to you the fluctuations that the people considered, and I want to hear you. What do you think? What kind of fluctuations are those? Quantum fluctuations, you will answer to me, okay, I thought are statistical fluctuations. I think are, but now I think that are quantum fluctuations. So tomorrow we're going to see the distinction between them and try to study in the inflationary paradigm how the structure emerge. And for today, I want to hear the questions, please. I don't know if there are questions. Okay. Don't we define uncertainty with respect to a certain eigenstate of the system? Don't we define uncertainty with respect to a certain eigenstate of the system? Okay, in quantum mechanics, you have a operator, an observable, for instance, the energy, and the people said, okay, you have an operator, or the angular momentum, the position is an sorry? Go ahead. Okay. You have an operator, an Hermitian operator, and the theory said when you perform a measurement on the observable, you have a particular, a well-defined value. So in that case, you have an eigenvalue of that observable in a particular eigenstate. I don't know if your question is regarding that or is in that sense, but you have when you have a wave function in general, you have a wave, and the weight of the wave function we think is thought as a quantum fluctuation, in the sense that you have an uncertainty, because you could have all the possibilities for each values in the middle. And if that is your question, I agree with, or the answer is yes, you can define the uncertainty on the wave packet of as, because you don't know, or you don't have access to know what is the value in the middle of the weight of the wave function. More or less, or if you want to, or tell me if I didn't understand properly your question. Okay.
Well, people are too quiet, so let me ask one question. So hopefully it will encourage people to break the ice here.
Okay.
When you showed the Harrison Zadovich formula for the power
Power spectrum.
Yes, exactly. Yeah, so that's astoundingly simple, right? So Is it
Right.
really a power law, or is it just for
The
a
power law.
leading
Yes,
term?
simple. It's
Yeah, but
simple. I know. It's really. I feel your question because the first time that you thought, okay, I look forward to see what is the power spectrum, and it's a power law. Oh wow, maybe one expects more elaborated form, but no, was astonishing for the people that this simple form could explain the differences in the temperature.
well, but that could
Using
be.
this, yes, using the expression, and they also try to, if the people, I only know the arguments, but Harrison and Seldovich try to explain, for example, the distribution of black holes with this relation. They have many arguments to explain that the distribution is codified with this form, not with the last, but with this form, they try to study the distribution of black holes in galaxies, and also how the distribution evolves with time.
I see.
And
So for the CMB, I would have been extremely surprised that this formula works, because then you could see that this is only what I'm seeing from the CMB is only the leading order in wavelength, right? So in high wavelengths.
right, it's the only important feature that they take for the data, and they connect using this form. It's not nowadays they have more. The cosmologists work with this expression using different ends, but at the end is almost the same expression. And with this power law, they study how the temperature is, what is the causal connection between the different points in the CMB and the whole sphere. But with this law, if you want to add more precisely, you need to take n close to 0, but not exactly 0, but at least you need this expression with n smallest, but is almost similar to this. Maybe the people that perform the computational part were not agreeing with me, because I know that moves this n change all the codes and the computational, the numerics part. But in terms of the form, it's essentially the same. And with this form, they explain the distribution of the matter and the distribution of the particular objects that I mentioned, and the correlations and the temperature. And also tomorrow, I'm going to explain briefly that using the quantum effect, the people again get this expression.
Very well.
So,
Thanks. Very
so
looking forward to it.
yes, yes, because the people have two ways to get the same spectrum. So, and beyond the ways that we have to obtain, this spectum works better with the observation. So yes, I know, I understand your the feeling of your question.
No, thank you. That's fascinating. More questions, people.
Let me know if you think I was not clear in one part, or I don't know if I speak really fast in the topics. Let me know, please.
Maybe I'll ask a second question, if I may. My second question is, when you mentioned that people were taking these statistical averages in thinking of an ensemble of universes,
Okay.
what's the measure they use? In other words, are they integrating over a particular variable with the physical interpretation?
When the people talk about the assemble,
Yeah,
or
so
can you
the overline of a symbol, you denoted in a
repeat?
statistical average, right? So
Right.
yeah, so I'm asking the measure they're considering to take this average, or
The measure, yes, there are in the mathematical sense. What is the measure that they use to
yeah,
perform
well,
the
I see.
integrals?
Yeah, yeah, that's one interpretation. Another interpretation would be just this multiple universes are, they must have something varying between them, among them, right? So
Yes,
each
yes,
universe would have a value for some quantity, what
right.
this quantity would be. So that would be my question.
Ah, okay, yes. I don't know. Let me say something, and at the end, tell me if I understand the question. But they take into account the fact that when you perform many measurements, for example, in the case of, to say something, they try to read the density fluctuations in how they perform a measurement several times, and they take the assumption that each time that they perform the measurement is considered as a measurement in a different universes, in the sense that several measurements could could work or could explain in terms of ensembles, in terms of the ergodicity, that the measurement, the perform several time a measurement could explain as the measurement on assembles. I don't know if I
I see.
explain
Yeah, so
more.
it's what they probably see space-time fluctuations and they represent them as statistical
Yes,
fluctuations instead.
yes, they try to read the with the data, extract the values, and then they build an assemble and name possible universes, in the sense that they took into account the several data from the observations in this way.
Very good, thank you. I think there is a related question in the chat. So someone is requesting to explain again what space-time fluctuations are.
Can you explain again the space and fluctuations? Yes, yes, maybe. It's a question related, as you mentioned, because space-time fluctuation describes how a quantity change from one point to the other. So if I have a glass and I measure the temperature, okay, a glass is a small object, but if you consider, for example, a big object, the temperature on the earth, and you measure the temperature in Brazil, and then compare with the temperature on Mexico City, the differences is basically the differences give us the space-time fluctuation, the differences on the temperature, because you are thinking in a quantity in one point and compares with a different point, but with the same quantity. And then also you can think in terms of the space-times, the full space-time. If you try to get a quantity in the full space-time and then compares in another point, you obtain the space-time fluctuations. And it's different, for example, with in the case of the density relative density perturbations. Here we can think that the people consider the space-time fluctuations, but when the people work with the assemble, now you have at this point the two kinds of fluctuations in the same equation, because in this quantity that now is not generic, is the density. If you put here the density, you consider the space-time fluctuation, but when you put this line that represents the average, you are considering the statistical fluctuations, because now you have an ensemble of universes. So in that sense, I mentioned that the Harrison-Seldovich spectrum consider both the power, sorry, or in the power spectrum, the space-time fluctuations and the statistical fluctuations. Okay, I encourage you to ask questions. Maybe if you want to read first the full presentation, I can send you the presentation, but tomorrow it's really important for me that at this point we're clear, because tomorrow I'm going to introduce the quantum treatment on the inflaton, and we started to work with the notion of quantum fluctuation. So at this point, for the work on Harrison-Seldovich, they consider statistical and space-time fluctuations. But tomorrow, we have a new element, the quantum fluctuation. So we have to do the distinction between them, and at the end of the tomorrow's lesson, I'm going to put the theory in a way to read the problems that inflation have, or what is the reason, because many people try to develop a new paradigm to explain the expansion in the formula of primordial structure before to explain the other kind of things in the theory. So it's really important for me that you ask questions. If tomorrow you don't have questions, if today you don't have questions, tomorrow you can ask me. Okay.
Yeah, despite this warning, I don't see any questions in the chat left. So perhaps people can ask you in the beginning of tomorrow's lecture if there's any point that is not sufficiently clear.
Yes,
so for today, let's thanks Rosa again for her lecture, and I'll see you all tomorrow.
Thank you.